What I'm going to start talking about before we get to the actual beam behavior of reinforced concrete, I'll talk about just the general nature of design in reinforced concrete. Now, many of you have already taken, a portion or about structural steel design. And you know that there's a couple different philosophies that they use in structural steel. Allowable strength design, ASD, LRFD, load and resistance factor design. In concrete, we use a philosophy that's called strength design. Okay? So the American Concrete Institute, the ACI, in their building code is called ACI 318. They have a philosophy that they use, and that philosophy is called strength design. So you can go to this building code. You can go into, in fact, I'll bring in the building code and show it to you how it's set up. It's set up a little bit different than the steel manual is. But the building code espouses a philosophy of design for all reinforced concrete members that they call strength design. Okay? Strength design has been around for a very long time. I mean, back in the 1960s, they were actually starting to bring out and roll out strength design. So by the 1970s, when I was in school, they were talking about strength design. A precursor to that sort of was, called working stress design, which was sort of similar in form to allowable stress design, but they haven't used that for years and years and years. So strength design's been around for a pretty good while. For you all, since most of you are familiar with steel and LRFD, strength design looks a lot like LRFD. Okay? So, without getting knee deep into all the minute details of how this philosophy was formed. For those of you that are, again, familiar with LRFD when you took steel design or you were studying steel design concepts, you can think of strength design as almost the same thing. The nomenclature and the symbols that they use will be the same. And that's, I think, probably the lion's share of the work for people trying to learn is, well, hey, if we're using the same symbols, that might, that makes my life easier. Strength design basically looks like this. You have a capacity of a member, and again, you could call that the design capacity of a member. And that design capacity has got to be greater than or equal to a required capacity, or we might call required factor, or in concrete, a lot of times they call this the ultimate. So, for instance, if we're talking about bending moment design of a beam, we could say the design bending moment capacity of my beam should be greater than or equal to the required bending moment that's on the beam. Now again, what do you have? I think for people learning this, the thing that they got to remember is, where does the design capacity, or what factors influence the design capacity? Where does the design capacity come from if I'm talking about a reinforced concrete beam?
Different lengths.
It'd be what?
Different lengths of a beam, I guess.
Not lengths of the beam. It'd be what?
Loads are put on type.
No, that loads and stuff would be this. When you're talking about the required moment that the beam must have, that's where the load, this is the load side of it over here. And really, when you're talking about the length of the beam, if you're talking about bending moment, that's how long it is, and the loads that are put on it, and where the loads are put on it. That's what's going to generate the bending moment. So, length of the beam, what your loads are, where the loads are. If you're talking about bending moment or shear on a beam, that's this place over here. That's going to give us the required bending moment. Some people might call it the ultimate bending moment, ultimate moment. Okay, but what goes into design capacity? How much capacity does my beam have for bending moment, let's say? How about size of beam? You know, how wide it is, how deep it is. What else? Concrete, since it's monolithically cast, it's not too much like steel. Like steel, we worry about lateral bracing. Because concrete, just by the nature, we don't worry a whole lot about that. How about the steel that we use? How much steel? What type of steel? What's the area? How strong the steel is? How about how strong the concrete is?
So the mix.
Huh?
The mix.
Well, yeah, the mix, how strong, F prime C, that kind of stuff, how strong the steel is. So all those factors fall in over here, okay? So, think about this. One side of this is the member, how much capacity it has, what it's made up of, how big it is. The other side is going to be loads. How big are they, where are they, so on and so forth. Okay? If we were going to write this in symbol notation, and we were talking about bending moment, which is going to be our first topic, the design capacity for bending moment on a reinforced concrete beam is going to be given this notation, phi mn. Where have you seen that before? Steel. If you're looking at steel and LRFD, that was the notation, wasn't it? Phi is what we call a resistance factor. Where's phi going to come from? Yeah, from the book, from the code, it's going to be given to you. What about Mn? Nominal moment capacity. Where's that going to come from? Formula, right? There's going to be some formula we learn. We say, hey, here's the formula for nominal moment capacity. Is that virtually the same as what you did with steel? In a general way? Yeah, it is. That's got to be greater than or equal to mu. Where have you seen that notation before? Well, steel, when you're doing LRFD. U, again, stands for ultimate. Some people like to think of it like that. But what mu really means, and with steel, remember how the thing, when we generated mu, maybe mu was given to you, but when we generated it, it was generated using load factors, right? Load combinations and load factors. Those combinations, those factors still exist, okay? We could go give you the code, and you could look at the code and say, yeah, hey, here's what we're doing. We're doing all these things. We're going to shorten that process and just tell you the basic load combination is 1.2 times the dead load plus 1.6 times the live load, which again, for those of you that have studied LRFD and steel, that was the most common combination. All right? Now again, the only thing you have to remember about the combinations is that the loads, whether they be dead, live, whatever, they got to be service loads if you're going to put them in there. We're factoring the loads up. All right? So those have to start out as service loads. So again, you hear the term service. Service means unfactored. Okay?